Okay, so one last little talk here for CS 151. Today we're going to look at sorting algorithms. It's a companion lecture to searching algorithms from chapter 18 of the textbook. So just like searching for an element, we often need to sort items in a collection of data. And that's useful for doing things like making alphabetical class lists, ranking the results in the tournament, figuring out who won a particular contest, or who got the most points on a computer game system. And basically we can do this with either array-based or linked lists, and sorting can also be done on a variety of different data structures. So let's take a look at some of the specifics of sorting. Early estimates indicate that about half of the time that we spend on computers was spent sorting, and the other half was spent doing other things. Like searching, we consider that sorting takes place on items in memory. If you want a full comparison of sorting beyond this chapter, which is chapter 18, not 8, take a look at Knuth's Art of Computer Programming, volume 3. It's a pretty comprehensive treatment of it. It's a very, very detailed book. So our favorite is bubble sort, or was selection sort. If I ask students to implement bubble sort, they'll implement selection sort. If I ask them to implement selection sort, they'll implement bubble sort. So this was one of our favorites. So suppose we have a list of n elements 0 to n minus 1. And in the series of n minus 1 iterations, what we do is we compare the successive elements, and if we bubble them up, basically we take the greater one and swap it with the smaller one if the greater one occurs before in the list. So here we have a list 10 and 7. 10 is bigger than 7, so we swap the 7 and 10. Now we move up and compare 10 and 19. 19 is bigger, so we don't need to swap. Move up 19 and 5. 19 is bigger than 5, so swap them. And then we have 19 and 16. Well, then we swap the 19 and 16. And then we repeat that until we get the largest items bubbling up until the end of the list. So how good is bubble sort? It's pretty easy to implement. It's one of the nice things about it, and that's one of the reasons we covered that one in CS 150. Basically, we go through the list, and while the list is not in order, we go and bubble those items up, starting at 0 and then going all the way to the ones that haven't been sorted. So you can see 2 for loops nested there. That's going to kind of lead us to the fact that this is O of n squared. So it contains those nested loops. The outer loop executes n minus 1 time, and for each iteration of the outer loop, the inner loop executes a certain number of times, and we get a total of O of n squared comparisons. And the number of assignments in the worst case, where everything has to bubble up until the end of the list, is O of n squared. So a lot of times we're interested in the worst case scenario. So how about selection sort? Was this our favorite from 150? Again, if I ask people to write bubble sort, they end up with selection sort and vice versa. So selection sort was another favorite from CS 150. And here what we would do is we go through the list, select the largest item or the smallest item, as the case may be, and move it to either the beginning or the end of the list, the sorted portion of the list. So we go through, find the max or find the min, and then swap that element with its proper place in the list, depending on whether you're sorting ascending or descending order. So this is the code for selection sort, and again, you can see kind of those two nested for loops, and heuristically this is going to give us an idea that this is O of n squared. So it does 3 assignments n minus 1 times, so we have a total of 3 times n minus 1, which is 3n minus 3. That's O of n assignments, and the number of key comparisons is O of n squared. So we do n the first time, n minus 1, the second n minus 2, the third, plus all the way down to 1. So when we add that up, we get that well-known formula, n times n minus 1 divided by 2. And that gives us O of n squared for this. So another favorite introductory sort is insertion sort, and this is kind of what you do when you're playing a hand of cards. Basically, to sort the unordered list, you remove all the entries, you insert them, the first one into initially empty list, and then keep the new list in proper order according to the keys. At each step, the first unsorted item is put in its proper place. Now, to do this, you need to move some of the sorted items down. And we do this a lot of times if we already have kind of a sorted list and we just want to put something in there. So let's take a look at how this one would actually work. So we start out, we have these list of critters, and the first one we have is hen, so we just go ahead and put hen into the list as the first item. The next one we encounter is cow. Cow comes before hen alphabetically, so what we need to do is we need to move hen down into the second place and then insert cow. Third one we get is cat. Cat comes before cow, so we need to move cow down one and hen down one, and then we insert cat into the first one. The next one is ram, and ram comes after cat, cow, and hen, so it just goes right in the fourth one. We're not doing any data movement in that case. The next one is ewe, and it comes after cat and cow, but before hen, so we have to move hen and ram down, and then in that empty space we insert ewe. And last but not least, our favorite, the dog. It comes after cat and cow, so we need to move ewe, hen, and ram down, and then we insert dog into the list. So this is the code for insertion sort. I don't think this is one we cover in 150 very often, but it's a fairly simple sort to get working. And you see, again, two nested loops here. There are four in a while. So that's kind of going to lead us to the surmise that it's O of n squared. Again, that's a heuristic. It's not a hard and fast rule. The best case is that the list is already sorted. And basically, in that case, we only require n-1 comparisons. And it ends up being O of n. The worst case is for each iteration, we have to move all of them. And the if statement in that case evaluates to true, and we get O of n squared key comparisons. The average number of key comparisons and item assignments are both O of n squared. So for these basic sorts, if you summarize them, bubble sort comparisons is O of n squared, swaps is O of n squared. Selection sort, number of comparisons is O of n squared, and swaps is O of n. So it's slightly better on the swaps. Insertion sort is O of n squared and O of n squared for both comparisons and swaps. So out of these, selection sort is kind of the most efficient based on the number of swaps. So some more advanced sorts, these work on the idea of divide and conquer, and you're going to see these in CS 321 then. So the main idea is to divide two lists at each stage of the process, and do this until you get a list of size 1. And a list of size 1, hey, even I can sort that one. So you sort the lists that are of size 1, merge them back up into lists that are of size 2, and then make sure those are sorted. And you do this going all the way back up the same way that you do with a tree. So you break it down and then build it back up. So let's take a look at two of these divide and conquer approaches. One is merge sort, which chops the list into two sublists that are nearly equal size. You may have an odd size list. You sort them separately and merge the two sorted sublists into a single sorted list. Quick sort, basically here we choose a key from the list, and we hope that it's about at the midpoint, that half the keys will come before and half of them after. And we call this key the pivot. We partition the items into two lists, keys less than and more than the pivot, and then sort the two reduced lists separately and then merge them back up, put the two sublists together. So for merge sort, consider this initial list. We chop it into two lists. We'll make the left side slightly larger. So on the left side, we'll take 26, 33, 35, and 29. And on the right side, we'll take 19, 12, and 22. So working on that left side, we break the list down into 26 and 33 on the left and 35 and 29 on the right. Then we take 26 and 33, break it down. Hey, I can sort 26, I can sort 33. And on the right, I break it down into 35 and 29. And then we merge the lists at each level. So On the left-hand side, we get 26 and 33, and on the right, we get 29 followed by 35. Then we merge those back up, 26 followed by 29, followed by 33, followed by 35. Then we would attack the right-hand side in a similar manner. And graphically, this is what it looks like. The ones in the left are the unsorted, and as we go down the tree, we break them in half each time. So you can see each level of the tree, it breaks that list in half. And then going back up the tree, the numbers in color are the lists that have been sorted. So here, we go all the way down. We get that 26 followed by 33, 29 followed by 35, then 26 followed by 29 followed by 33 followed by 35. And we would do the same thing for the right-hand side of the tree. And at the finish, we have our sorted list. So that's merge sort. Quick sort, using the same list, we pick a pivot. For simplicity, we'll pick 26. Just pick the first one. Sometimes you want to pick something near the middle of the list. There are different strategies for picking those that you'll get into in 321. We divide the list into ones that are less than or greater than the pivot. So the ones that are less than 26 are 19, 12, and 22. The ones greater than are 33, 35, and 29. The pivot goes into neither list. We apply recursively, and so the first one we would pick 19. We would basically have 12 and 22. 12 is less than 19, 22 is greater, and 19 is our pivot. And then we would merge these lists as we go up the tree again. And then we would work on the greater than side and continue to break down and then merge the lists as we go back up the tree. So here's what it would look like. We partition the list into 19, 12, and 22, and 33, 35, and 29 with a pivot of 26. Again, we picked the first one as the pivot here. We would sort 19, 12, and 22, which would mean that 19 is our pivot, and 12 and 22 are the two sublists, and then we would combine those into 12, 19, and 22. Then we work on the right-hand side, 33, 35, and 29. We pick 33 as our pivot. 29 goes to the left. 35 goes to the right. We combine back into 29, 33, and 35. And then we would combine the two lists, the 12, 19, 22, 29, 33, and 35, with the initial pivot of 26. And we have our sorted list. So that's how quicksort works. So quicksort's kind of a really nifty way to do things. So quicksort, the average case is O of n log n, which is kind of the speed limit for sorting with a sort based on key comparisons. In the worst case, if you pick a really bad pivot, you pick the worst one each time where you only get that pivot on left and everything's greater on the right, or vice versa, then you basically end up with selection sort. Merge sort is always O of n log n, and that one uses the divide and conquer and sorts the sublist and then combines those into one sorted list. It differs from quicksort in how the list is partitioned, because we get those two sublists of nearly equal size, not based on the pivot. So quicksort, if you pick a bad pivot, you can get O of n squared, but you'd have to pick a really bad pivot, but it's worth looking at the worst case. So the number of comparisons, the average case is O of n log n, and the worst case is O of n squared for quicksort, and the number of swaps, the average case is O of n log n, and the worst case is O of n squared. So in summary, sequential search searches the list and makes this is back to the searching. Sequential search makes O of n. Binary search is if you have the list already sorted, and that one is O of log n. It's 2 times log n minus 3. Binary search is the optimal worst case algorithm for solving searching problems by using the comparison method. To construct an algorithm that's less than log n, it can't be comparison based. So it's kind of like, hey, if I know where something is, I can find it, type of thing. That can be a calculation-based one. If we know where things are in the list, we can get better than log 2n. But if it's comparison-based, you can't do better than binary search. Sorting summary, bubble sort, selection sort, and insertion sort are all of O of n squared key comparisons, with selection sort having O of n item assignments and the other having O of n squared item assignments. Quicksort and merge sort work by divide and conquer, partitioning the list. Quicksort, the average number of key comparisons is n log n, and the worst case number of key comparisons is O of n squared. With merge sort, the number of key comparisons is always O of n log m, which is a nice property to have. When you're looking at algorithms, compare their use of space, computer time, how much effort it's going to take, statistical analysis. It's interesting to see how these perform on different types of data sets. Empirical testing results, benchmarking of these algorithms can be important as well. And, last but not least, ease of implementation. Sometimes, hey, I need to get this to work el pronto. I can program bubble sort just like that, whereas I might have to look up merge sort. I'll, get it to work right away using bubble sort, and then later on, if we're going to use this code in a production environment, I'll get it to work with merge sort. Your final choice depends on the length of the list, size of the records, how you represent them in storage, and mean performance is important, but so is the standard deviation. You don't want it to vary too much in how well the algorithm performs. So I think that about wraps it up for CS 151, and you'll get more of this type of stuff in CS 321 and as you go on in the program. Thanks for watching. Thanks for hanging out with me this semester.